Hello everyone. This is the second lecture in week 3, and this lecture will deal with Bayes' theorem. As we saw earlier, Bayes' theorem is useful to update probability, but generally we use it just to flip conditionals around. So we saw earlier that probability of A intersection B is a product of two probabilities, one being a conditional probability, A given B times the probability of B. But since probability of A intersection B is the same as probability of B intersection A, we must have probability of A given B times probability of B must just be equal to probability of B given A times probability of A, and that leads us to Bayes' theorem. And as I said, we usually use this to flip conditionals around. So if I know probability of A given B, and I'm asking for the probability of B given A, I can use this formula to compute the probability of B given A. So I guess maybe without more ado, let's just go straight to an example. This refers back to example 230, which is the one about the nuclear power plant getting funding depending on which party gets in. So the question now is, if we know that the project received funding, what is the probability that the Conservatives got in? Why you wouldn't know that is an open question, but let's assume that you've been hiking in the jungle, you receive word somehow or other that the project received funding, but you don't know which party got in. So you're now computing the probability that the Conservatives got in. Well, we know the probability of funding given the Conservatives, but now we want to find the probability of Conservatives given the funding. So we're going to use Bayes' theorem. So probability of Conservatives given funding is equal to the probability of funding given Conservatives times the probability of Conservatives divided by the probability of funding. Actually, you can kind of see here, we've got an initial probability of Conservatives getting in, and we're going to update that probability given additional information. So given that we receive funding, what is our new probability that the Conservatives got in? So we can see that this updating of the probability is working even in this problem. And that's what I'm saying right here. What is the posterior updated probability of Conservative getting in given the additional information that funding took place? And then this probability of C is a prior probability of C of Conservatives getting in. So we knew that we were told originally probability of C getting in was 0.15. That's our prior probability. And we knew that probability of funding given the Conservatives was 0.4. We computed last time the probability of F, which we need here. That's that thing underneath here. In the previous example, we computed that by adding up the branches leading to F, and that added up to 0.6. So we get probability of C given F is probability of F given C, which is 0.4, times probability of C, 0.15, divided by 0.6, and that has changed now to 0.1. It was 0.15. So given funding, we've reduced the probability of the Conservative getting in, and that basically makes sense because they had, I think it was the lowest probability of providing funding. So the fact that we got funding means that it's unlikely that the Conservatives, less likely that the Conservatives got in. Well, we can do the same thing by looking at the Liberals. Probably that the Liberals got in given funding is going to be probability of funding given Liberals, which was 0.6, times the probability of the Liberals getting in, which was 0.55, divided by the probability of funding, which is 0.6, and that's 0.55, and that's exactly the same. That's sort of basically because the probability of funding given Liberals and the probability of funding overall will happen to be the same. How about the NDP? Well, we know that this probability of NDP getting in given funding must be 1 minus the sum of these two. This is 0.65, which is 0.35, or we could compute it as probability of funding given NDP, which was 70%, times the probability of NDP getting in, which is 30%, divided by the probability of funding, which is 0.6, and that works out to be 0.35. It was 0.3, it has actually gone up, and it's gone up because the NDP was the most likely to provide funding, so the fact that we got funding suggests a stronger possibility of the NDP getting in. Okay, another example is as follows. Let's suppose 3 different companies supply microprocessors to a computer firm. And the firm has established the following information over the years. So we have three source companies, and source company 1, the fraction of defectives is 2%, and they supply 35% of the microprocessors. Source company 2, fraction defectives is 1%, and they supply 50% of the microprocessors. And source company number 3, fraction defective is 3%, and they supply the least to the company, and justifiably. Presumably the company still buys from these people probably because their microprocessors are cheaper and they can live with the higher fraction defective. So let's define some events. Let's let C1 be the event that the processor came from company 1, C2 the event that the processor came from company 2, and C3 from company 3. And let's finally define the event that D, that the processor is defective. To answer the question that's being asked, which company did it most likely come from? So we've selected a microprocessor, tested it, and found it to be defective. Now we're looking for which company did it most likely come from. So we're looking for the probability of coming from company 1, 2, or 3, given that it's defective. So I'm looking for something like this: company that is coming from company I, given defective, and for I equals 1, 2, 3. So for this, we need, first of all, compute the probability of defective. That's the denominator in this Bayes' theorem expression. So let's draw an event tree. We've got 3 source companies, and we know the fractions coming from each source company, and we know the fraction defective from each source company as well. So I'm looking for the probability of D, so it's the probability of going this path, or this path, or this path. Add up all these probabilities: 0.35 times 0.02, 0.5 times 0.01, and 0.15 times 0.03, and I get a probability defective of 0.0165, or was that 1.65%? Okay, so now I can plug those results into this calculation here. First of all, for C1, so the probability that it's coming from company 1, given defective, is probably a defective given company 1 times the probability of defective 1, and I can see that from the tree here. That's probably a defective given C1 is 0.02, and probability of C1 is 0.35, divided by total probability of defective, 0.0165, and I got 0.42. Do the same thing for the C2. C2, I see the probability of defective is 0.01, that's this number, and probability of C2 is 0.5, divide by 0.0165, and I get 0.3. And then I repeat for C3. Probability of defective given C3 is 0.03, that's this number, and the probability of C3 is 0.15, this number, and I get 0.27. So given that it's defective, it most likely came from company C1. Does that make sense? Yeah, C1 has a reasonably high fraction of defectives, and it's the second highest fraction supplied. But we see C1, well, they're a little bit different. C1, C2, 0.37. The reason it's lower for C3 is because the fraction supplied is quite a bit lower. Okay, so let's look at another example. Let's suppose that a city's air pollution is caused by industrial and automotive exhaust. Let's let C be the event that car exhaust pollution is controlled. That's automotive exhaust pollution. And I be the event that industrial exhaust pollution is controlled. So C and I are that we control the pollution from these two sources. And let A be the event that air pollution overall is successfully controlled. It is estimated the probability of controlling car exhaust is 0.6, and industrial exhaust is 0.75. If only one source is successfully controlled, the probability of successfully controlling air pollution, event A, is 0.8. And then we ask some various questions. Well, in this case, C and I are not disjoint. I'm assuming that we can control both car and industrial exhaust. So we end up with a Venn diagram that looks something like this. These events C and I overlap. That means that we need 4 branches, one for each disjoint area in this Venn diagram. Outside, C alone, C and I alone. So that's C intersection I, only C, only I, or neither, everything outside. And from each of these, we've got a branch A or not A. That means I successfully control overall air pollution, or I don't. So the next thing we have to do is label this event tree with probabilities. So in order to do this, we need to make some assumptions. Let's first of all assume that C and I are independent, which may be reasonable if different government departments are responsible for each. The reason for this is that somehow or other we've got to be able to compute things like C intersection I, and all we know is probability of C and I. So if C and I are independent, it's just the product of these. We do not know probability of C given I. So if they are dependent or not independent, we cannot proceed. So if we assume independence, then probability of C intersection I is just the product of these two things. Okay, then the other thing is the statement, if only one source is successfully controlled, it means this, that probability of successfully controlling air pollution, given that either we only control car or we only control industry, is 0.8. But the problem with a given that is when you have an or, it's not given information. We're not sure which one of these take place. So I take this to mean that I get a probability of successfully controlling if I control C alone or if I control I alone. And these probabilities are both equal to 0.8. I also need something else that is not given to the question, but I'm going to assume that if both car and industrial exhaust are controlled, that air pollution is controlled. So that probability is 1. And the other thing is if I don't control either of them, the probability of controlling air pollution is 0. So I've got this set of information about the probabilities now of ending up in this part of the tree. These are the conditional probabilities given C and I and so on and so forth. Other required probabilities are the first part of this tree, so these probabilities here, and they come from the idea of independence. So C intersection I is the product of probability of C and probability of I, and that's 0.45, and I can compute the rest of these probabilities just by multiplying the appropriate probabilities. So this gives us a labeled event tree that looks like this. These 0.8s are the ones that I assume, probability of A given that only C is controlled, or the probability of A given that only industrial is controlled. So then we have a series of questions that we can ask. What is the probability of A, basically? Probability of controlling air population. So that's the probability of arriving here, or here, or here, or here. And I can get that just by adding up these probability of 0.45 times 1, 0.15 times 0.8, 0.3 times 0.8, 0.1 times 0. And let's see if these numbers are here. 1 times 0.45, 0.8 times 0.15, 0.8 times 0.3, and 0 times 0.1. And that gives me 0.81. If the air pollution is not sufficiently controlled, so this is given a complement, what is the probability that the fault is due entirely to failure to control automotive exhaust? Now this is a little bit tricky. We're trying to find, given air pollution is not controlled, what is the probability that it's only due to inability to control, a failure to control automotive exhaust. In other words, we controlled industrial exhaust. So it's the probability of not controlling automotive exhaust and controlling industrial exhaust, given that we failed to control the air pollution. Well, Bayes' theorem tells us this. The probability of this is probability of A complement given this first part times the probability of the first part divided by A complement. And we know these bits and pieces. We know the probability of A given C complement intersection I. That comes from, where is it? A given C complement intersection I is this one, 0.8. So its complement is 1 minus 0.8. Probability of C complement intersection I is 0.3. And probability of A complement is just 1 minus 0.81. And I get then 0.32. Next question is, if air pollution is not controlled, so again, given A complement, what is the probability that control of automotive exhaust was not successful? So this is another more complicated problem. we're looking for a probability of that we fail to control automotive exhaust given that we fail to control air pollution. But we don't have a probability of C complement in terms of A complement anywhere. So we have to make use of the fact that C complement is actually made up of two parts. There's C complement, let's go back to my Venn diagram. Okay, so I'm looking for probably a C complement is going to be made up of everything of this part, C complement intersection I, and C complement intersection I complement. So it's everything outside of C. So there's two parts, this part here and this part here. And that's what I'm writing down here. Okay, so C complement is C complement intersection I union with C complement intersection I complement. This is everything outside, and this is everything outside of C, but inside of I. So then I can write this thing as the probability that this takes place given A complement. And then I look at this and this. Are they disjoint? Yes, they are disjoint, so I can write this as the sum of these two probabilities. And now I have to use Bayes' theorem on both of these things. So it's probability of A given this times this divided by this, and so on and so forth. These numbers are all just coming from given information, either from the event tree or from given information up here. These values plus these values. Okay, so we can put the main trick at this part is to recognize that C complement has to be made up of two areas coming from our original Venn diagram, which is composed of a bunch of disjoint areas. Then what are we looking for? Control of what was not successful. I don't think I was asked this one. It's probably that given we were not able to control air pollution, what is the probability that we were not able to control industrial pollution? It's exactly the same one, except in terms of I complement this time. Plug it all in, we get 0.68. Okay, and that concludes this lecture. Thank you for listening.